Um, okay, so today we're going to be talking about simple approaches and models. One sec. There we go. Okay, so last time we were talking about doing sort of simple trends and forecasts, and so we're going to sort of continue in this path, but starting to think about sort of sustainability issues, thinking about particularly emissions for climate change. So we can think about different ways of kind of taking this trend here and sort of continuing on. Yeah, and so as we were saying before, oftentimes what we're trying to do here is use historical information to kind of project future trends. In the topic of like climate change, this becomes particularly sort of difficult, right? Because the historical trends that we have for like CO2 emissions are like increasing, and we want to start to change that. And so as you introduce things like interventions, right, then doing simple sorts of projections and forecasts start to fall apart. And so you need to start thinking of sort of different approaches to being able to do forecasts and predictions and that sort of thing. Okay. So what kind of simple approaches can we take to do projections and analyze energy use and greenhouse gas emissions? So what these sort of simpler set of models are going to do are to look at the sort of drivers behind energy use, behind emissions, and start to sort of tweak those a little bit so that we can not only develop these, I guess what I would call business as usual cases, but start to look at intervention cases. So we'll look at energy demand projection methods, GHG drivers in different use sectors. We'll look at a couple sort of high-level examples of decomposition methods. So actually probably all three of these are somewhat related to that topic. We'll look at Ghg mitigation options. And then lastly, looking at sort of accounting / stock turnover models. This is particularly useful for and sort of tied into the last bit of last week's lecture where we have technology adoption. This is a way to sort of take those forecasts and start to inject them into sort of your overall fleet. So if I'm talking about, to give a more specific example, if I'm talking about like adoption of electric vehicles, last time we basically looked at these diffusion models in order to see how quickly they're sort of entering the new market. With stock turnover models, you're able to figure out the proportion of the entire fleet that would be, electrifying. And then you can use that information to then do other sorts of calculations. Okay. So the simplest options, so this goes right in line with what we were talking about last time. So this would be a measurement that would sort of extend any particular sort of historical curve, right? And so this is an extrapolation based on simple growth rates. So this is the amount of energy in time t, and the amount is just based off of some baseline energy in whatever baseline year, and then you have some growth rate to the power of t. So this is essentially some kind of exponential growth rate. You'll see that this is much more of, as we'll describe in a second, a top-down model, right? This doesn't, this growth rate term encompasses or is meant to essentially encompass all of the driving factors behind energy growth. So that might be like having a higher population, having more people have access to energy, you know, technologies, increasing energy usage or decreasing with energy efficiency. All of those factors are kind of just combined into this growth rate, which we represent as being able to capture all these things based off of like historical trends. And then if you want to kind of take apart that assumption about your growth rate, then we start to decompose that demand into things that we think are driving energy. And so the first sort of simplest form, okay, if we think that the strength of the economy, for example, is related to it, and then the energy intensity, we can have these factors where you have you know, GDP and energy intensity. So when you do a forecast into the future of this compared to this, instead of trying to derive a single growth rate, now you can have projections of your GDP, which might be related to a different growth rate and energy intensity, which would have its own sort of measurement. And so if I want to do GDP into the future, it could be the same thing where I have GDP-T equals GDP0 times 1 plus R to the T. You could have that tell you sort of what this term would look like in the future, except now your growth rate is specific to things in the economy, and you have the flexibility of like, maybe I want to change the growth rate for energy intensity to be, you know, somewhat different, or maybe I want to make it so that the energy intensity is, for example, increasing at a or decreasing at a different rate compared to GDP. So this decomposition is starting to get a little bit sort of more and more complex. Any questions about that? So you can continue this sort of trend, and we can, you know, break these down into many sort of factors. Generally, we think of these as econometric approaches. So a lot of times, the calibration of that parameter of the growth rate, for example, might be something that you would try and calculate historically. And so I can start to expand that term more and more to encompass like specific drivers that I think are important to energy usage. So in this case, you know, I have income elasticity, energy price elasticity. And again, we would be using historical data to estimate changes in demand. So the thing about these top-down models, right, to reiterate, they ignore the structure of energy demands. So a lot of these models, again, will start to break down if you have introduction of like structural changes. So one example of that would be, so if your energy prices have some kind of trajectory in the past, and then now all of a sudden I want to introduce more expensive technologies that might be cleaner. So let's say I want to buy a bunch of like offshore wind farms that happen to be a little bit more expensive. That might break the sort of trends that you would be able to derive from the historical data, and then this sort of model starts to fall apart a little bit. So you need to be careful in doing these sort of top-down projections that the historical trends are able to try and capture exactly what, particularly if you're introducing interventions, that you want to make sure that you can sort of account for that in these models. But usually these types of things, particularly in the like econometric context, are more useful for business as usual cases. All right. Yes. Yeah. Yeah, so it gets a little tricky here because, like, let's say we're back in 2010 and I want to do this type of analysis. The historical precedent for like charging infrastructure, it's just zero, right? There's like no stations in 2010, there weren't any stations in 2009, and so on and so forth. So if I were to extrapolate that, right, it would just be zero sort of all the way through. And so particularly for these types of changes that are newly introduced to society, this kind of approach really wouldn't work. But once you're sort of at a point where you have some information about it being introduced, like if I were to do that analysis now, then I'd be able to look back over the last decade and see how charging infrastructure has installed, right? And then I could take those trends and kind of extrapolate them out into the future, right? And so this is tricky because the timing of the context of that problem really matters. So 10 years ago, I would say, no, this would be a bad approach to do that particular question. But now I would say, okay, we probably have enough data where you could get pretty decent extrapolation of like charging infrastructure installation. Yeah. Yeah. Okay. Yeah, so the first two classes of these projections assume the changes in the future will be similar to the changes in the past. Okay. So the sort of key part of this is figuring out the correct sort of parameters to extrapolate. There are upsides and downsides to this. Using empirical data is typically a pretty strong indicator for empirical indicator for being able to estimate trends. And this is good. This is particularly good when you don't have sort of interventions. If we're thinking in the context of like climate change, you might say, well, okay, why is this useful? Because we want to, we still want to, we want to introduce interventions to kind of change our projections and trajectory of like CO2 emissions. But doing baseline scenarios can be really useful, right? We could, for example, show policymakers like what happens if we keep going the way we're going. Okay, and so there's a lot of important analysis that still kind of uses these sorts of extrapolations. Again, hard to predict discontinuous events. What happens if like a new technology is suddenly discovered that has big implications for changes? Obviously, you wouldn't be able to do that in these types of models. Yeah. Okay. Any questions? So the other type of forecasting is based off of what we call bottom-up. So this is where we're instead of looking at sort of general trends to project energy use, for example, we can look at really specific engineering or end use models to explicitly consider changes in technology. And so this might be something like, okay, what happens if I were to introduce like a new technology like electric vehicles into the market? What would the energy use be corresponding to that particular technology? So you could have some kind of end use. So this would be characterized by the I in the summation. So this, for example, if this energy demand were all of transport energy demand, each I could indicate all the technologies for light duty vehicles and all the technologies for medium and heavy duty and rail and airplanes. And each of those you could have, okay, what's the total number of people who are doing light duty vehicles? What fraction of them would be driving the electric vehicles? You know, how much would they be using it, and what's the sort of energy intensity? So this is like a really ground up way of pointing at like exact technologies and being able to shift numbers specific to that. And so essentially what we want to do is decompose the demand for basically every end use. Yeah, and so this is particularly useful for looking at technology change scenarios and being able to get at some of the incremental energy energy changes. The demands and the correlated emissions are better understood at a more disaggregate level in these types of models. So in this way, we can have a much more detailed representation of energy use. Some of the weaknesses, okay, so subject to forecaster's bias, I don't think that's that distinct from top-down models necessarily, because oftentimes those will have some kind of biases of their own. But it can be harder to do certain aspects that are stronger in sort of top-down models. Oftentimes engineering analyses don't always do like economics and prices. So that can be tricky. Oftentimes you're kind of exogenously sort of introducing certain types of interventions without necessarily doing economic analysis about whether or not, for example, a technology will be will actually be adopted. The other thing is that these are good at sort of disaggregated levels, but if I want to understand the implications in across the sort of whole economic sector, it's a lot harder to get right. You're essentially saying, okay, I'm going to break down to these individual factors, and I'm going to add it all back up to sort of the entire economy, and you will probably have a really hard time getting the sort of correct aggregate numbers. And so those are some inherent drawbacks with sort of getting down into the weeds for particular technologies. Okay. So yeah, let's take a look at some examples of this. So if I were looking at something like fuel economy, we can still think about something like this in the context of like top-down versus bottom-up, right? And so a top-down example would be, okay, I'm going to look at a lot of the sort of trends here, and I can just look at how those lines are kind of sloped, and then figure out like a regression parameter and do projections of how those lines might extend out into the future. So that's a way of doing like a top-down kind of approach for this. A bottom-up approach might be more like, okay, I can look at the sort of suite of available vehicles. What sort of technologies they have in them, and then let's say I introduce like lightweighting or something, or a particular sort of technology, figure out how that changes the energy efficiency, and then sort of recalculate the change. So we can look at sort of underlying drivers or overall trends in fuel economy. Okay, and I should just mention this is a sort of linear decrease here because this is using units of liters per 100 kilometer versus here, this is fuel economy as we sort of do it in the US, which is miles per gallon, which is the inverse. So on the left-hand side, going down is better for fuel efficiency, and on the right-hand side, going up is better for fuel efficiency. Did we talk about this at all? The Mpg illusion? No? Okay, so like, all right, here, I'll do a quick. This is a very sort of counterintuitive thing between these two measurements of efficiency. So this is something that I like to try and have people keep in mind when they think about this. All right, so I'll just quickly draw an example here. Okay, so let's say we have two cars, car 1 and car 2. Can you guys see over there? Yeah, okay. So car 1 is 40 mpg and car 2 is 20 mpg. Okay, so what I'm going to do is I'm going to make an improvement of this car of 10 miles per gallon. So this goes up to 50 mpg. And for this one, I'm only going to do plus 5 mpg. So this goes from 20 to 25 miles per gallon. Okay, so raise your hand if car 1 saves more gasoline. If switching from 40 to 50 saves more gasoline, or does switching from 20 to 25 saves more gasoline? So plus 10 mpg versus plus 5. So raise your hand for car 1 switching. Raise your hand for car 2 switching. Okay, so you want to explain why that happens?
I just have a feeling that because it's a greater ratio.
Yeah, okay. So I probably tipped you off when I said Mpg illusion, but okay. Usually people get this wrong. And actually most people do, like when people don't actually do this type of calculation when they go to like buy cars, and it becomes really sort of less straightforward. So let's say I want to drive 100 miles. Okay, so in car 1, I start at 2.5 gallons at 40 mpg. And then I go to 2 gallons at 50 mpg. So that's a savings of 0.5 gallons. So for car 2, it's 5 gallons at 20 mpg going to 4 gallons at 25 mpg. Right, so it's 100 divided by 40, 100 divided by 50, 100 divided by 20, 100 divided by 25. So this saves me 1 gallon of gasoline. So even though this increases the mpg by double this saves twice as much gasoline as this switch. Okay, and the reason for this is because Mpg is an inverse. It's a 1/x type of thing. So if I care about consumption, then it's a lot more intuitive to do measurements where your consumption is in the numerator. Yeah, and so the way that the US measures fuel economy is really counterintuitive when we think about fuel consumption, unfortunately. Does everyone get this? All good? All right. Okay, so back to this. We'll think about this still in the context of Mpg here. So the problem with one of the problems with the top-down approach when it comes to Mpg, if I were to look at this trend compared to many other countries over this time period from the 1980s to the mid-2000s, you can see that fuel economy was pretty flat, okay? And so there wasn't much improvements happening in fuel efficiency technologies, or so you would think. Okay, and so this is one of the things that might be sort of easily looked in a sort of top-down view at a sort of technology-specific level. So in actuality, at the same time that miles per gallon was sort of relatively flat, so what other things affect fuel efficiency? Sort of weight, power, and sort of improvements in transmission. So generally speaking, right, the heavier the car is, the less fuel efficient it is. You have to move more mass. Yeah, go ahead. So that doesn't matter. It's more sort of generalized improvements in efficiency of transmission, and that can happen in both sort of automatic or in manual. Yeah. Generally, the higher power that you have, sort of all else equal, the lower your fuel efficiency as well. And so if I look at trends in, for example, weight and power, you can see the weight increases and that the acceleration is improving. So this is 0 to 60 times. So the lower this is, the higher the higher the acceleration. And then, oh, okay, actually, so I guess I misspoke. This is percentage of cars that are manual. So there are improvements in the transmission, but overall, automatics are more efficient than manual. So if you have more automatic transmission vehicles, then you're also improving fuel efficiency. Yeah, so that's what this is showing as well. So you can see that the weight is increasing, and you can see the acceleration is improving, but the Mpg is staying flat. So in actuality, there is a whole bunch of innovation happening in improving fuel efficiency of vehicles. You just don't see it. They're kind of putting it into other attributes of the vehicle. And so, you know, because there is this sort of higher preference for things like having higher horsepower, having larger cars, automakers have concentrated more efforts into sort of doing these types of things while sort of trying to maintain the fuel efficiency of the vehicles. And this is shaped by, you know, what people want, or maybe what automakers tell people that they want. And it's also shaped by policy. So we're going to talk about this in a later lecture, but fuel efficiency, there are these fuel efficiency standards that basically require automakers to build cars to meet some kind of average fuel efficiency. And for a long period of time, sort of during the 90s and early 2000s, so the sort of like Clinton, Bush Jr. era, a lot of those standards were basically kept flat. And sort of following that time period, in the first Obama term, they introduced these new fuel efficiency standards, which have since improved fuel efficiency. But yeah, so going back to this idea, looking at weight and power, we can see that efficiency per unit weight has improved substantially over time, just even in the time period where the actual fuel efficiency of the vehicles was flat. And so automakers making larger cars, people want more, they were moving more from, you know, sedan size vehicles to crossovers and SUVs. But the fuel efficiency would still be kind of the same. And the fuel consumption per unit power, you can see here, same type of idea as the power increased, they kept fuel consumption relatively flat. And so per unit power, sort of you still are seeing these improvements. Okay, and so this is a sort of nice sort of contained example of how you might want to apply sort of bottom-up models. If I want to decompose to these particular attributes, I can then look closer at these trends and be able to extrapolate some of these things and say, let's say I want to stop sort of improving power, like how could I then shift some of these technology improvements in efficiency back into what we would observe as sort of like aggregate efficiency of the vehicles. Yeah, and so if I assume that the other attributes are not increased, I can then take the trends that I see in fuel efficiency improvements and be able to do sort of new sets of projections. And this is essentially kind of what happened following the sort of new CAFE standards under Obama. A lot of researchers and yeah, people in the industry were able to do these projections and say, okay, well, if the automakers kind of focus their technological improvements into strictly fuel efficiency rather than improving power and making vehicles bigger, you know, we can have a sense of kind of what this looks like. Yeah, and so these are emissions performance standards. So these emissions and fuel efficiency are sort of directly linked. So you can do measurements of emissions impacts of fuel efficiency improvements. Okay. Any questions about this example? Yeah.
What do you think drives the desire for a bigger faster vehicle? What I'm asking is, we're trying to make it more efficient, but also it seems like we're not.
Yeah. So automakers, so in my opinion, I think a lot of the demand is sort of just driven by automakers, no pun intended. Yeah, yeah. So like, for example, like if you went into the 2000s, yeah, I remember looking at this when I was in grad school. If you go into like the 2000s and I look at like all the commercials during, say, the Super Bowl, like how many of those car commercials are promoting things like power and sort of like larger vehicle sizes like trucks and SUVs and that sort of thing, versus sort of post introduction of CAFE standards, all of a sudden you have some commercials promoting things like fuel efficiency and like and green vehicles and that sort of thing. And I think that there are ways that they can shape the demand, and there's also the way that they provide supply. Whatever cars are on the lot are essentially going to be sold. And I mean, there are some dynamics with how consumers will respond, but I think that automakers have they have a lot of power in being able to shape the demand that people have for particular types of cars. At least that's my opinion. I hope I don't get in trouble for saying that. It's going to get posted to YouTube, but oh well. Yeah.
One thing I want to say is that there's kind of perverse incentives involved because the larger vehicles have higher profit margins.
Yeah. Sorry, I was actually gonna say that. Mention that.
So in terms of like American policy, the three major American automakers, they all make
Larger
profits on trucks.
Yep.
So if you're a policymaker in America and you want to affect those vehicles, what you're going to ultimately affect is American jobs. So it's one of these things where it doesn't look good if you're a senator or a president and you say, we need to be taking less trucks and less SUVs because what that ultimately means is union jobs in Michigan or whatever. And really, who cares about those jobs? But politicians do. So.
Well, the jobs part is probably a little bit less straightforward, but yeah, I think the thing on the profit margins is definitely true. And we'll actually look at some of this when we start talking about the policy specifically. But yeah, there is this incentive for automakers to produce these larger vehicles. If I'm Ford, I make a lot more money selling an F-150 or some kind of minivan compared to if I were selling a sedan. And in fact, Ford, like what, a year and a half, 2 years, actually probably more than that now, they essentially sort of canceled production of most of their small vehicles. Yeah, I would say like 90% of their sort of smaller vehicle segments are sort of slated to retire. Ford. Ford. Yeah.
Also, like this way, a lot of that commodity safety because they have their cars.
Kind of. Okay, so this is an argument that gets thrown around a lot. So yes, true, generally, but in reality, yeah. So there have been some studies that have looked at this. The biggest metric for safety as it pertains to weight is the weight differential between vehicles. So if you have a truck versus a car, the truck always wins. The proportion of morbidity and mortality and how it's skewed is mostly dependent on the weight differential between two vehicles. And so if all vehicles are really heavy, then yes, right? Then it's safer to kind of bring up the weight of lighter cars. But then the same is kind of true if you bring all vehicle weights down. You are not really sort of decreasing safety for those types of collisions. Yeah.
I think the ones right now, I drove over, if handling rate though in like lighter SUVs?
Yeah, so it's the sort of there are all these different factors that go into it, but like far and away the most important one, it's just like a simple physics thing about mass. So rollover stuff is important, and that will play into like safety ratings of vehicles. So you know, two cars that would have the same weight, but one might have like a lower center of gravity, then technically those, you know, one will be rated safer than the other. But at the end of the day, like by far and away the biggest factor is weight differential. For rollovers though, electric vehicles tend to be really quite a bit better, actually, for safety in general, because the batteries are heavy, and so there's more mass. So that helps with the weight thing. And then the center of gravity is usually a lot lower because batteries are typically stored in the bed of the vehicle, so it brings the weight closer to the ground. Yeah. So like Teslas have actually been, from the sort of NHTSA safety rating perspective, have been like by far the safest vehicles ever produced. It's very difficult to roll over an electric vehicle that has like more than 200 miles of range, because there's just so much mass in the battery. Okay, so let's get back to the sort of forecasting thing. So we were looking at this particular example in fuel economy standards, but there are lots of sort of challenges. You know, if I wanted to do sort of projections based off the historical, so this is, someone did this retrospective look of emissions forecasts. So there's this thing called the annual energy outlook. So this is something put together by the Energy Information Agency in the US. And they do these sort of economy-wide projections of the energy sector, all sorts of things. If you guys haven't actually used this before, you know, I would highly recommend looking into it as like as a sort of general resource for a lot of historical and projection information. And so every year they release this annual energy outlook, and they have all the historical values, and they also have projection values. And so if you do this retrospective and I pull out, let's say, the total CO2 emissions in the US from energy use, if you looked at the AEO in 1999, they had these projections look like this. And then the next year, right, they had new projections that look like this, and sort of, you can see what happens with actual emissions. It changes like this. And every year, you know, their projections are kind of off the mark, right? And so, you know, you can look at some of these historical retrospective analyses and see how well people do when they actually do these sort of forecasts. And actually it tends to be sort of not so great. But that isn't to say that these models aren't useful in sort of their own way, right? Oftentimes these sort of projections here going out into the future, you know, they'll have specific parameters associated with why that's happening. And so, you know, this can be a sort of benchmark of saying, you know, if these things happen, then this might be what your emissions look like. And so even if you're sort of getting it wrong, that doesn't necessarily mean that all of this sort of modeling effort is useless. But it is definitely challenging. Here's another one. where forecasts of LNG imports. So I'm picking this period where the US was more reliant on imports of natural gas, right, before the big sort of fracking and shale gas exploration happened in the US. And so what ended up happening, so here's the black line is the actual, and every year they would have these sort of projections going out, and they would sort of decrease every year as they adjust to sort of the new reality of natural gas fracking and extraction in the US, and they would sort of lower this every year. And so you can see, right, prior to sort of knowing about that technology, you know, your forecasts are going to be really sort of poor. And as you get more and more information about it, maybe they'll start to do a little bit better. But this is the sort of inherent challenge in doing these types of analyses, is that these structural changes can really kind of mess up your forecast. So who knows when the next sort of thing will happen, right? So it's hard to make predictions, especially about the future. Yeah.
Is there a way that you can account for structural challenges
So if you can,
historically,
yeah.
or is there some sort of factor?
Yeah, so we'll talk about that right now, actually. But generally speaking, like if you can see it coming, then I can think about how I might change my modeling, you know, alter it in some way to accommodate that. But the challenge is actually being able to see it coming, right? Like being able to know that, oh, there's this new technology about fracking that's going to let us extract, you know, much more natural gas than we ever thought possible in the US, and therefore decrease our exports, or sorry, increase our exports, decrease our imports, that whole thing. So if you have some idea that it's going to happen, then yeah, you can adjust for it in the model. But the hard part is like being able to have that kind of insight. Okay, but let's actually talk about exactly this idea about how you might be able to do these sort of forecasts. So this is thinking about scenario analysis. And so the way I like to think of this is, so being able to illustrate ideas and options, and then amenable to analysis and evaluation. So things where you kind of just qualitatively describe what might happen in the future, I'll maybe describe this as like a story. Okay, and then sort of on the other end of the spectrum, ways that I can sort of really quantitatively be able to describe and evaluate something. Okay, so you have a lot of analysis and evaluation, so these are models. And then when you combine these two, you can think about sort of introducing a quantitative assessment of the sort of stories, okay, that you tell. Okay, so scenarios are essentially stories that describe some kind of plausible future. We want scenarios to include some kind of quantitative components, and then sort of multiple scenarios to describe different sorts of futures. And so, you know, back in the 2000s, if I had this idea of fracking and being able to do all of this stuff, then I can then turn to some of the modeling tools to figure out, as a scenario in the future, what might happen to sort of natural gas usage in the US. But that might not be the only scenario that you think of in this sort of analysis. And so this is the thing that lets us capture sort of structural changes explicitly. And so when you delve into the world of like climate change mitigation and adaptation, like it is sort of rife with scenario analyses, because this is how we address sort of uncertain futures and how we introduce things like structural changes into modeling efforts. So if you think about what for example, the IPCC does, so that's the Intergovernmental Panel on Climate Change. They release these big reports every couple of years on climate change. They have all these sort of different scenarios of climate change hitting sort of different temperature impact or temperature changes and all the sort of things associated with them. And those are all fundamentally examples of scenarios of possible futures. So it requires the developers to think about really carefully and explore all the sort of drivers within the story that you could then sort of measure quantitatively. We can see on sort of this scale, I think this is provides some sort of nice structure to things that you might want to think about when you do scenario analysis. So more generally, like we want to be able to include the things sort of higher up in the importance scale. And then the difficult part is that things that have a lot of uncertainty about, how would you go about sort of measuring these sort of critical things that are sort of high on both of these axes. Okay, so let's think about a couple sort of stories. And as we go through these, maybe we can think about some areas where you can start to do, you can start to introduce this quantitative modeling aspect into it. Okay, so there's this one sort of story, you know, people get smarter. And so we might envision this world where, okay, lots of people do, you know, public transit. You have these much more sort of local, you know, sustainable agriculture. What else do we have? We have people starting to act to save the environment. And so, you know, behavioral changes that might relate to prefer sort of cleaner energy sources. Here, people stop using gas cars and move more towards, let's say, biofuels or hydrogen or electric vehicles. Okay, and so this is, you know, I'm telling this sort of hypothetical story, but in each of these things, you know, I can figure out some kind of way to introduce quantitative methods, right? So here, this might go back to accelerating a diffusion growth curve for your alternative fuel vehicles. Here, you might do like higher shares of cleaner transit options. You know, for this one, maybe it's about, you know, supporting like more or cleaner electricity co-ops that have sort of higher proportions of renewables, right? And so I can start to think about sort of remolding this story into specific, like tangible, quantitative measurements. And so that's how you would turn a story like this into a possible scenario where we might call this like an optimistic scenario where people try really hard to fight climate change. You know, you could have the sort of opposite thing. Okay, state of fear, people will start hoarding gasoline. Okay, no immigrants. All of this thing, and then you have sort of higher, okay, you know, higher water usage for, you know, centralized mass agriculture. Again, you know, this is a sort of really contrary scenario to the story that we were just telling, right? But again, as I think about each component of this sort of story, I can start to think about how I would model that. And okay, last one I have, too little, too late. So this might be the sort of most apt for continuing like baseline projections. We can think about sort of just extending the trends for like gentrification and sprawl, trends in specific improvements of vehicle attributes. Let's say that we still didn't care about fuel efficiency. It's all about vehicle power and size and that sort of thing. So again, in comparison, right, all of these three stories are things that we could imagine are sort of possible futures. But in order to understand the impact of each of these types of futures, we have to introduce the sort of quantitative analysis that then let us turn these stories into like real scenario analyses. Yeah, and so I don't know, it seems like sometimes it seems like these, you know, stories are somewhat arbitrary, but at the end of the day, like when you do these sort of future projections and forecasts, analysts are essentially kind of making up what they think is going to happen, right? And so none of these are necessarily wrong in the strictest sense, right? But it's more about what is sort of driving our assumptions, and it's important to try and accommodate the future uncertainty in a robust way as possible, and that often means having to do like looking at a whole range of different scenarios. Yeah. Yeah, I mean, that's one way you could do it. Like you can think, you know, if I were to talk to a different person or different types of people regarding what they think is going to happen in the future, you're probably going to come up with a whole bunch of fairly different answers. And so oftentimes, you know, those types of ideas can help be starting points to derive these initial stories. Oftentimes, you know, it wouldn't be, maybe I wouldn't say it would be even something that you would need to get from like the general public. Like if you were to ask, you know, in my field in transportation, if you were going to ask a whole bunch of different people what they think like the dominant technology might be in the future, you'd probably come up with a couple different answers. And so, you know, you might talk to someone who thinks hydrogen is going to be the big future of transportation. And so that would dictate, you know, its own sort of story and scenario, versus if you were to talk to someone else and they say, actually, I think electric vehicles are going to be sort of the big future, right? And that would lead to a sort of different scenario. So yeah, I think having some sense of, even in the expert community, the sort of variation in what people think is going to happen is useful to try and address the like full scope of possible futures. Okay. Anyone else? Yes.
Is there like a specific methodology to follow to kind of create these scenarios, or is it more like, you know, be engaged in the sector and like did review, say a couple of news and like go to conferences, and so that way you're kind of very informed about and just choose what you.
It's definitely more of the latter. I think it's not something that's so sort of straightforward where we can sort of systematically say, you know, look at these exact things. It's going to be sort of really context dependent. I mean, this is kind of why, well, hopefully a lot of you guys are in grad school, is you're really diving into the sort of expert community on a lot of these subjects, so that you kind of have a picture of a lot of these future trajectories in your own mind. So yeah, being able to understand what people think, why, and what goes behind a lot of these things are going to help sort of develop your ability to construct like good scenarios in the future. Okay. Okay, so let's talk about some decomposition methods. So we're going back up to think about sort of this combination of sort of top-down and bottom-up approaches, where we're looking at higher level factors that still let us do interventions in particular areas. So what are some factors that determine greenhouse gas emissions? So for example, for you guys, what are some like key choices and decisions that might influence energy use and carbon footprint? Yes.
The temperature corrections that I see on the heater that I'm looking at, what temperature.
Yeah, okay. So yeah, heating and cooling, thermostat usage. Anyone else? Yes. Yeah, okay. So that's like your travel demand, essentially affecting your travel demand. Yes. Yeah, so that's one of the bigger ones, right? So yeah, choosing to eat a sort of vegetarian diet, there are a lot of greenhouse gas emissions associated with raising of like cattle and livestock. Yes.
What kind of vehicle I want to travel in? Like
Yep.
using a public transport versus driving my own car or biking?
Yep. Yep. That's right. So hopping on the bus or biking is going to be is usually going to be cleaner than driving. Yeah.
Rate of consumption of stuff, like clothes.
Yes. Rate of consumption of stuff. Yes. Generally speaking, yeah. Yeah. The sort of slower you have that sort of turnover, all the embodied like energy and emissions, producing that stuff, that rate will decrease. Yeah. Yeah. Well, it's materials, but it's also related to like everyday use. So if you're living in a smaller room, right, the energy that it takes to like heat and cool that room is lower. You know, the amount of like lighting that you have in a big house compared to a small, like the. Yeah, so the material stuff, I mean, any material use will have some embodied like energy and carbon associated with it. So generally speaking, you know, like a big house, the initial construction of it will have like a higher environmental impact than something that's smaller. But the sort of ongoing energy use, I think, is important as well. Yeah.
So another factor would be,
Yeah.
Where has that stuff been produced, right? Is it part of the complex supply chain, or is it, your neighbor's backyard?
Yeah, exactly. And so, you know, Is anyone taking Alyssa's class, LCA? Yeah. So they cover a lot of that sort of thing that's based off of the sort of life cycle of a product and the associated like energy and emissions with that. So yeah, that definitely will make a difference as well. Okay, and so I can generalize a lot of these things that you guys are talking about. Most of it is having to do with the examples that you guys are giving is having to do with sort of activity and consumption, right? And so this is like your transportation mode, you know, size of homes, the amount of energy consumption, right? That might be related to heating and cooling or other factors. There are other things that affect us, so that might be a little bit less in your control. Well, so energy intensity somewhat in folks' control. So if you have, especially for demand side efficiency, and so this might be like if I were driving in one type of vehicle and I changed to a more efficient vehicle, right? Your energy intensity could improve even if your activity or consumption doesn't change at all. Energy supply efficiency. So this could be related to like if a power plant upgrades to a more efficient turbine, right? Then the efficiency, the energy intensity of it would improve. And then you have carbon intensity, and this is usually what we associate with like fuel choices. And so if you switch from one fuel to another, one example of this might be if you switch from a gas water heater to an electric water heater, that's a fuel switch that has implications on the carbon intensity based off of sort of upstream activities, well, particularly for energy intensity. And then generally speaking, your population, right, also plays a role. So the more people that you have doing all of these things, the larger the sort of overall footprint is. And so we can think about modifying, you know, each of these factors. With a lot of the things that you guys were saying, we could be modifying activity or consumption, but we can think about, you know, other ways of affecting other factors. So this is known as the Kaya identity. It's a form of multiplicative decomposition. So we think about breaking these down into connected drivers. So this is like one of the simplest frameworks that people have used to understand what levers that we have in changing emissions. The general way folks have, or the way that people have sort of generalized this equation is to represent in really simple terms, sort of activity by economic activity per capita. So that's this one here. Energy intensity is represented by energy per unit of economic activity, so energy per GDP. And then carbon intensity is the CO2 emitted per unit of energy. So that's the GHG per energy here. So if you multiply this across, right, population cancels out, GDP cancels out, energy cancels out, and then you get a measurement of the total emissions. So this is a simple way of decomposition to calculate emissions across your sort of entire sector. So in a similar way, this is an alternative decomposition method called IPAT. This is actually quite old, comes from this idea that the impact that you have, in particular with pollution. So this was sort of prior to a lot of the sort of fundamental concerns about greenhouse gases and climate change, they were thinking more about local air pollution. We can think about the population times the consumption per capita times the pollution per production of whatever set of goods that you're talking about. So the kaya is related to this sort of initial instantiation of decomposition breakdown. So really sort of simple approach, thinking about population and consumption. Yeah, go ahead.
Really thinking both of these, where do they factor in? But if we do, where do they factor in emissions from the grid and actual production?
Yeah, okay. So for example, in this previous one, we might think about energy and carbon intensity as the two big ones. Not everything is going to be derived from this. You can think of these terms as encompassing everything in the economy, but actually the vast majority, okay, I'll say the sort of non-transport side of things, this energy intensity would probably represent sort of the average energy intensity of the grid, and then the no, okay, wait, that's not right. Energy intensity would represent sort of the amount of energy being used for all the end use services, and the carbon intensity would represent the translation of that energy demand into carbon emissions coming out of the grid.
So I was just thinking about how for fuel switching in particular, if you go from gas to electric for appliances, it's better to do that in California where it's a greener grid rather than like the Midwest where there's a lot of coal.
Yeah, so the issue with this is it's super aggregated. It'd be harder to see like such a specific type of signal. You'd have to think of it how the combination of these two things would change in the aggregate in that particular example. But yeah, if you were to sort of be able to calculate the delta in carbon intensity as you did something like that, then you'd be able to absorb exactly what happened. It would probably just be tricky to see something so specific in here. Yeah. Oh yeah, okay, so I'll mention that when this equation was kind of first derived, people mainly viewed population and consumption per capita, and actually mainly this affluence idea as the sort of levers to improve pollution, and that technology, this pollution per production type of thing, was viewed as the sort of big problem. But nowadays that's shifted, where we think of this as a potential area for improvement. Oh, yes. Sure.
The middle one, the consumption per capita, the affluent.
Yep.
So they're taking as a given that the more affluent the more.
Yeah, that's right. But it doesn't have to be like that. I think this was just their way of kind of measuring it. The idea is that, okay, like in general, we observe that affluence is correlated with consumption, right? But we can change that number so that you can decrease the sort of relative consumption per capita, but it's not necessarily like you're trying to make people less affluent. It's just about decreasing the sort of demand from those sources. Yes. so generally in this context, you can think of it as this sort of aggregate measure for like energy, okay? And so consumption of energy matches production of energy. And then there's some like carbon intensity associated with production of that. Does that make sense? Yeah.
There was a move that that's when people or vice versa can decrease the carbon footprint.
Yeah, that's the idea here, is that to decrease pollution, you need to affect this measure of affluence, and the way that you would do that is to decrease the relative amount of consumption. Yeah. Okay. So the Kaya parameters. So population and activity are your primary socioeconomic parameters. GDP per capita. This is kind of what I was mentioning before about affluence. It's just a measure of the economic activity, but it doesn't necessarily correspond to like the well-being of those individuals. And so you can think of levers to improve activity as we strive to decrease the sort of relative, I guess, economic activity, but without affecting the well-being in sort of a negative way. And so that's kind of the inherent challenge of taking sort of measures against climate change is, you know, people don't want to go bankrupt paying for electricity bills that are higher because you're adopting more sort of expensive but cleaner power production, right? So that's sort of just a generic example of you know, the types of things that we have to think about as you affect activity. You want to try and improve things like energy intensity and carbon intensity and activity without sort of detracting too much from individual well-being. Energy intensity and carbon intensity are usually the factors where you're going to affect them through technological change. Energy intensity depends on types of consumption and production and energy technologies within whatever sector you're looking at. And then the carbon intensity depends on sort of the resources and sort of primary energy that those resources are derived from. This is a useful way of getting a sort of high level look at possible interventions within the context of like economy change. And so you can look at policy levers that affect reduction of activity and consumption. You can look at different policy levers that may improve energy conversion and end use efficiency, and then policy levers that might do sort of fuel switching. There are lots of different policies that exist that address all three of these. So like fuel switching, for example, like the low carbon fuel standards in California is a nice example that's sort of looking directly at this. Improving energy conversion and end use efficiency. So in the early 2010s, there was a ban on incandescent light bulbs, on production of incandescent light bulbs, which caused a switch to CFLs and ultimately LEDs. And so this is a policy, right, that is really sort of aimed at improving sort of end use efficiency. Okay, policies that might affect activity and consumption. What is an example of that? like the flex your power thing in California. If folks were here a couple decades ago, that was actually a big sort of intervention to decrease consumption that worked quite well. Basically this thing about like turning off your lights and not running the dishwasher and your laundry and certain times. Okay. There are some easy calculators for this type of thing. For the chi equation, I would encourage you guys to take a look at this, and you can play around with the parameters and you can see how things get affected. So projections of each of the chi parameters, what happens as I shift the population and economic output, what happens when I change energy, carbon intensities. They're really easy to sort of modify here. And then you can see a whole bunch of impacts associated with kind of your assumptions. You can also decompose this into different regions, and you can look at different time scales as well. So I can look at different areas I and different years T, and plug in potential projections for all of these things to have an understanding of what would happen with greenhouse gases. So this is a nice way, again, kind of to sum up, of being able to take what we would consider sort of essential drivers of emissions, do sort of these forecasts, and be able to have a quick understanding of what would happen to your greenhouse gas emissions. We can think about, in this context, like in the context of developing scenarios, right? I think it would be quite easy to come up with scenarios for like population and for GDP per capita, energy per GDP, all of these things. You could come up with historical or not. You could use historical numbers, derive baselines for each of these factors, and then sort of change them as you think about different scenarios to project out to and see what happens to your greenhouse gas emissions. Yeah, and so there are actually papers that do exactly this. There's a famous example of this published in PNAS, where they're taking kind of a relatively simple, equation and being able to look at how these drivers affect overall emissions. And you can play around with these levers to have like a holistic understanding of a bunch of different scenarios. It's not even necessarily saying like, oh, this particular thing is what's going to happen. It's more about, if these numbers are what they are, that I'm, assuming in the future, then probably our emissions are going to look something like this. And you can even come up with like a fairly reasonable set of like holistic ranges for future greenhouse gas emissions. Okay. Any questions about this? So other versions of decomposition, there's a couple of these tools that are basically the same thing, but could be, more sector specific. So for example, in transport, there's one that that's well known, 80 and 50, but then you can have specific decompositions within different sectors, different energy sectors. So for example, in industrial ecology, there's this type of decomposition focused on extraction, production, and use of materials. So it's exactly the same idea, except your equation looks slightly different. They have things related to specific materials. And so the equation might look something more like this. where you have material per GDP, pollution per material, and then the impact of that. So it's actually going a little bit farther. You know, in the Kaya equation, we sort of end up at this final thing of Ghg emissions. And in this case, they're looking at, you know, a specific impact associated with a type of pollution. And so that's something like a monetized health impact might be something that you would get out of this. Or even like a quantity of like morbidity and mortality. In transportation, there's this ASIP decomposition. It's a shipper model. This looks at your total transportation activity, modal structure, modal energy intensity, and then fuel carbon content. Gets at the same thing for greenhouse gas emissions. But you can see how now the activity, mode share, modal intensity, these are all things that are kind of specific with transportation technologies within the sector. And then there is another sort of decomposition method in transport sector called 80 and 50. And so this looks at, instead of that IPAT equation, you now have transport per person, energy per transport, and then carbon intensity. And so this is kind of like your activity, right? But it's specific to transport. It lets you kind of nail down some of these numbers with maybe a higher degree of accuracy. And it's it's a fairly simple model. You can do it in like a spreadsheet accounting model. And it allows you to be able to introduce specific transport technologies. You can imagine that if I were doing the Kaya equation and I wanted to focus on like transport, if I introduce like electric vehicles or something, and I'm trying to figure out, oh, how does that affect the like proportion of like energy and carbon intensity or even, you know, activity, that might be tricky to do because you're averaging it against everything else that's happening in the economy. And so when I take that same type of approach, but I go specifically into a targeted sector, I can take the same approach, but then as I do these sort of interventions, it's a lot easier to calculate these numbers. Okay. Yeah, and so general thoughts about specific things within the 80 and 50 scenario approach. You can think about different mitigation options. How much is it used? How much is it better than the current option? Again, these are factors that let you adjust those parameters in a much easier way. And the nice thing about this is it's quite clear to sort of understand thanks to its simplicity. Okay. So moving on from the decomposition methods, the last thing that we'll cover today are stabilization wedges. So this is a way to account for emissions reductions where we can split it into, I guess, these sort of manageable pieces. So this is another sort of simple approach that has been taken where we can look at individual interventions and how they might affect like a BAU business as usual curve. So if I look at my decomposition methods and I do a particular type of intervention, and then I can measure, you know, the greenhouse gas emissions reduction associated with that particular intervention, I can sort of stack that up against different sorts of interventions as a way of decreasing my overall trend. And so you can do this for many different technologies, and you can see okay, what would it take to essentially sort of stabilize fossil fuel emissions, for example, or even decrease them. So this is not like a typical projection approach. You start with some kind of goal, usually, well, in the context of a lot of these types of problems, it's usually about stabilizing it to flatten out. Sometimes you can have it decrease. You identify the actions that can be used to meet that particular goal. And then we think about the sort of feasibility of doing a particular technology. In that paper that's associated with this plot here, they identified sort of 15 potential options to use that could have these wedges that decrease your overall carbon emissions. So these are related to efficiency, technology, demand side reductions, and then on the supply side, improvements in like power plants, switching from coal to natural gas, CCS, which is carbon capture and sequestration. So a bunch of these different options, and essentially we can, in sort of discrete amounts, be able to reduce the emissions associated with your baseline scenario. So the value of the wedges, yeah, one of the useful things about this type of approach is that the framing of it lets you kind of tackle like a big problem like climate change into sort of more manageable chunks. This is really useful for like policy analysis, because if I go to my congressman and I say, oh, you need to invest like billions of dollars to fight climate change, that's going to be a lot harder to as a sell than to say, oh, you should invest in these specific discrete projects, right? And so by breaking it into sort of manageable chunks, this is actually very useful for policymakers to not only understand the specific impact of that, but how it contributes as a whole to like a broader plan to decrease emissions. So yeah, this sort of simple approach can have a sort of big impact, and the analysis isn't super sophisticated. Yeah. Yeah, and so we can think about what sort of wedges that are sort of more reasonable today. So we're a decade, or actually at this point, this is like 15 years later compared to when that paper was published, and which ones seem unlikely. So a lot of these things still are sort of on the table. Some things might be a little bit different. So like the technology, probably electric cars are considered to be sort of a more promising technology than hydrogen vehicles. Nuclear for coal, that's not happening so much. There was some thought in the 2000s that there might be a revival in nuclear power, but it seems like that's not particularly promising. The bigger trend is moving towards renewables. Yeah, and so many of these things still kind of hold true, but there are some specific differences with what they were saying in that paper. So synergies in mitigation options. Excuse me. So some calculations are path dependent. So this is important in thinking about the order in which you do the wedges can sometimes make a difference. So note that like if the way that we calculate is you cut activity by 50% and reduces emissions by 50%, But then if you then cut energy intensity by 50%, it only reduces based off of that new baseline. So compared to the original, a 50% cut in energy intensity only decreases 25% of the baseline emissions. This is kind of intuitive, but it's easy to get mixed up in this type of thing when you're actually doing the analysis. You don't want to be sort of double counting anything here. So this is just kind of a word of caution. So complex versus simple models, as I've sort of pointed out, all models are wrong, but some are useful. That's an important thing to keep in mind when you're thinking about your own modeling efforts, when you're thinking about evaluating other people's models. Very few people, like if I'm talking about doing some kind of forecast or predictions, very few people get it right. And when they do get it right, that's a lot of times just kind of luck of the draw. But we can think carefully about what is implied by any of these modeling efforts. And I think you can derive value in these things, even if the modeling ends up being incorrect. They can be sort of points in which to leverage for change, for example. Everything should be made as simple as possible, but not simpler. Simple models can be useful. They tell a simple sort of story, but they're transparent and easy to understand. So we will get more into sort of higher level systems modeling that's going to be more complex. And the complexity allows you to incorporate more details and processes if we want to talk really more specifically down to like engineering level of detail, that sort of thing. And that can incorporate a lot more of these sorts of details than the simple models that we talked about today can. But oftentimes you have to worry about things like the fact that it's a black box, which means, okay, you kind of have an input into the model and some output, but there's so much like complexity happening within. It can be hard to tell how certain things are happening and why. That's just sort of like you don't get to see the sort of inner workings of what's happening. And oftentimes you lose the transparency and understanding of why certain things are happening. Yeah, and I can definitely relate to that in doing some more complex modeling. Yeah, so if it's possible, you want to be this guy on the left, the simpler version. Okay, so we actually have one more set of things to discuss, but I am going to hold off on that. We'll pick up on that on Thursday's lecture. So we'll end a little bit earlier today because I know some folks have some questions about homework. So we'll leave some time to talk about that. So